When we are testing proportions, we're using this test statistic, our calculated z-value, where P1 and P2 are the proportions within each group. PC is the combined proportion. If my group sizes are equal, that's the average. If not, I need to calculate each one separately. And then N1 and N2 are the sample sizes, the number of people in each population group. This is the formula we used on Wednesday. But when we are actually deciding whether or not to accept the null hypothesis, reject the null, or not reject it, we're using a Z. What table are we using? A Z table, Appendix C. That's a normal distribution. What assumption are we making? That my proportions are normally distributed. I don't know that. How do I check that? We had a discussion about checking proportions for normal behavior in chapter 8. When we were doing this in the binomials, that's when we had a proportion, and we would check to see if that was normally distributed by checking something about the binomial samples, about what we actually had happen. But I have no idea what that is because that's our combined pooling proportion. The standard deviation was hard to calculate. We're using the standard error instead. You need to have a big enough group to be sure I have normal behavior. For proportions, what's my threshold number? 10. But it's 10 in the success group and 10 in the fail group. Now, When we were doing binomials, we thought about successes and failures. But I'm not talking about success and failure here in a proportion. I'm talking about the number of people that say yes and the number of people that say no. The number of people that say A is better, the number of people that say no, it's not. So these numbers are the numbers I get when I do the sample size. So proportion 1 is N1 over X1. Sorry, the other way around, X1 over N1. Wrong book. The number of times my thing happened, the thing I'm checking for, out of the total number. Well, then if I know what the proportion is and I know the population size, which I'm going to need to do for up here, I can figure out X1, even if I don't know it to start with. So for example, population 1 has a proportion of 0.3 and 50 people in it. Is that proportion normally distributed? To get X1, I multiply the proportion times the number of people. So X1 is 0.3 times 50, which is 15. And that means that N1 minus X1 is also bigger than 10. I have enough successes, enough failures, enough in each category for me to assume this is a normally distributed proportion. If we are not normally distributed, I shouldn't use a Z. Use something else. That's a major pain in the ass. So I'm probably not going to do that by hand ever. And that means I'm going to be using more powerful statistical analysis software like SPSS or something beyond Excel. The textbook uses this mini stats program, all sorts of different programs available. That means here, I'm going to use normally distributed ones. Then I can use the Z table. But it needs to be true in both populations, right? So what if I have my second population has a proportion of 0.25 and 48 people in it? Is that one also normally distributed? Because a quarter of 48 is 12, so X1 is 12, and the rest of it, that would be 36, right? 48 take away 12. Questions? Just like with a mean. If I'm doing a hypothesis test to say, hey, I think these things are equal, that's the flip side of saying I've got a confidence interval and 0 is in my confidence interval. 0 is in the confidence interval, then I could be confident that these two things are really equal. So we can build confidence intervals for proportions just like we built confidence intervals for means. I will again tell you, this is a big ugly, messy, nasty-ass formula. I don't want you to memorize it. But if I'm doing a confidence interval for a proportion, I start with my difference, P1 minus P2, and then I add or subtract based on my alpha over 2, my confidence interval area. But then I've got to multiply by the standard error, right? Standard error, like I said, was really ugly. So if I'm using a 90% confidence interval, then my alpha is 0.1. So what is z of alpha over 2? How do I find that number? By the way, a large number of you wrote that number down already on your formula sheet for the last exam. You've seen that number before. What is z of 0.005? Of 0.05? I'm hearing lots of different numbers pop up. The 1.96 goes with alpha being 0.05, not alpha being 0.1. 1.645. Now, I'm very happy to hear you rattle off 1.96 so quickly. If I don't remember, I go to the normal distribution because that's a z value, right? And I want that little bit to be size 0.05. Hey, look, 0.025, when it's quarter, that's 1.96. That's the one that's circled. But 0.05 is right between these two, between 1.64 and 1.65. So I'm going to have those numbers as the ones I most commonly use. They're the same numbers we were using for confidence intervals before. And then I can say, oh, I build the confidence interval. Is 0 in there? 0's in there. That answers my hypothesis test. Questions? I was able to test two means. Are they equal when my samples are connected or unconnected? So paired or unpaired. I was able to check two proportions. But something I really want to be able to check is variance. I want to know, is my sample consistent so that I can look at that normal distribution? So one of the things that we do a lot of is compare variances. A smaller variance, a smaller standard deviation, means more consistent outcomes. Quality control. You are making medicine. You really don't want a lot of batch variation, do you? I take this cold medicine, it does nothing. I take the same pill the next day, and oh my God, I'm knocked out on my ass, stoned off my gourd. Not a good idea, right? So I would like the medicine to be the same dose all the way across. I'd like it to be consistent. I need to know, is my standard deviation consistent? Small. So again, maybe you're not making medicine. Most of you are going to business, I presume. That's why this is the stats for business course. So what if I was doing asset allocations? I want to have a consistent rate of return. That means the variance in my rate of return should be small. Okay, there's a reason to understand this. Again, I'm going to try and do tests. And my tests are based off of my null hypothesis. I need to say, hey, I'm either going to assume that the first standard deviation is bigger than the second one, or the first standard deviation is equal to the second one, or that the first standard deviation is smaller than the second one. Now, I wrote down standard deviation. The textbook uses variance. Only difference is we square these numbers. Variance is the square of the standard deviation. Okay. If these are the null hypotheses, what are the alternate hypotheses that go with each of these? My alternate hypothesis. Okay. Does not equal. And now I can say, wait a minute, look at my alternate hypothesis. This is the left, so this is a left tail. This is not equal, this is a two tail. This is the right side, so this is a right tail. Interesting to me is that some textbooks don't actually compare the variances to each other, they compare the ratio of the variances. So take another look at this equation. I could say the same equation, sigma 1 squared over sigma 2 squared, bigger than or equal to 1. That would tell me the top is bigger than the bottom. Or here, sigma 1 squared over sigma 2 squared equals 1. Or here, sigma 1 squared over sigma 2 squared is less than 1. You'll see both versions in different places. But it's this bottom one that actually is the one that is easiest to test. A statistician by the name of Ronald Fisher looked at the way in which standard deviations and variances related to each other, and he came up with a different distribution, a different picture. Not our normal picture, not our student t distribution, not our binomial, not our uniform. He came up with a new picture. And he said, I want to use this. And since it was Ronald Fisher, we call it the F distribution. And we calculate an F statistic. An F calculation is S1 squared over S2 squared. But now I need two different degrees of freedom. Because there are two populations here, right? And since I'm looking at the variances, in my previous one, I was able to combine the standard deviations somehow. I need to keep them separate here. I need degrees of freedom for each population separately. And I'll just use one less. Just like we were doing last time, I'll use one less for my standard, degrees of freedom. And Fisher said, all right, just like in a z-test, I want to know if you're in the edge. For a right tail test, I want to know if you're in the right bit. In the left tail test, I want to know if you're in the left bit. If we're doing a two-tail, you could be in either bit. But the picture is very different. The distribution for F looks lopsided. And that's true. Because we're taking a ratio of things that are squared. It's always bigger than 0. So I end up with this squished towards 0 with a long one side and a very short other side. This is the F distribution. And again, I am 100% not going to expect you to draw this picture. But like with the normal distribution, picturing am I in the shaded area on the left or on the right is easy. Notice what is also on all of these. The Excel commands to get these numbers. Just like with a z-test, you need to know what the critical value is. So if you're smaller than the critical value on the left, then you reject. If you're bigger than the critical value on the right, you reject. If you're in that unshaded region in the middle, keep the null. There is a table in the back of the book. Again, just like with the normal table, just like with the t-table, there are F tables. And lo and behold, it's Appendix F. But we already have two numbers. We have degrees of freedom 1 and degrees of freedom 2, right? You know what's missing from all of that? Alpha. I need to know what my sensitivity is. How much am I pushing on this test? Now, in our textbook, there are separate tables for each alpha. Alpha being 0.10, alpha being 0.05. I think the third table is 0.01. No, it's 0.025. There is a table for 0.01. So there are a lot of F tables. So let me actually give you an example problem. Problem number 37. Problem number 37 says, here's the problem. Which samples show unequal variances? Use alpha equals 0.05 in all tests. I know which table to look at. Show the critical values, degrees of freedom clearly, and illustrate. They want me to draw a picture. Hell with drawing a picture. I want to understand what's going on. So, part A says my first standard deviation is 5.1, and I have 11 people in that group. My second standard deviation is 3.2, and I have 8 people in that group. My question is, are these variances equal to one another? Equal. Wait a minute. Which of the 3 kinds of tail systems am I using? One tail left, 2. 2 tails. Okay. That means my null hypothesis is that. My alternate hypothesis is this. Okay. I'm going to do 2 different things. The first thing I'm going to do is I'm going to go to degrees of freedom, and I'm going to go to the table on the back of the book. So what is DF1? What is DF2? Aha. N minus 1, N minus 1. So 11 minus 1, 8 minus 1. Okay. I go to the back of the book, and I find the 0.05 table. Now, here's where reading this table is weird to me. They give me the degrees of freedom for DF2 by row and by DF1 by column. To me, this is backwards. But I didn't make the table. I have to deal with it. That's why they say DF1 here and DF2 here. 10, 7. Which one's 10? Which one's 7? Okay, so 10, 7. F.0. Oh, wait a minute. Wait a minute. What am I doing wrong? I know what I'm doing wrong. I just caught it. What am I doing wrong? The 2-tail test. What am I doing wrong? If alpha is 0.05, I'm doing 2 tails, hash, I'm in the wrong table. So here's what I'm going to do. I'm going to write myself a note. 2-tail, F 0.025 table. So I turn the page to F of 0.025. Now, right table. 10, 7 gives me 4.76. I'm going to write that down. But let me go back to that picture for a second. Middle picture there. 1, 2, 3. Has 2 critical values. Which one did I just get? Gosh. the one I just got, is this one, the right one. They even call it FR. So I'm actually going to change that from F crit to FR. Now, because I'm using the table, it turns out that if you want to get the left version, you have to do two different things. I have to do 1 over the value that comes out of the table. But I have to switch the order of the degrees of freedom. So instead of doing DF1 and DF2 as 10, 7, this time I do 7, 10. I switch them around. So go back to the table. 7, 10 gives me what number? Say again? And then take 1 over that. Grab your calculator. So those are my critical values. Am I between? Or am I too small? Am I too big? I haven't calculated my test statistic. What's my F? My calculated F. S1 over S2 squared. S1, S2. Square there, or just do 5.1 over 3.2 and then square the whole blessed thing. What do you get? So here's my question. Do I keep the null hypothesis or do I reject it? Is this number too small or too big? Or is it just right? The Goldilocks number, isn't it? I'm keeping it. This number is not smaller than the left. It's not bigger than the right. We're in that middle unshaded area. We do not reject. We keep the null hypothesis. So I would like you to notice we said that the first group had a standard deviation of 5.1. The second group had a standard deviation of 3.2, but those are not different enough for me to say the variance in group 1 is different from the variance in group 2. I did also, on our Canvas page, do these calculations in Excel. So here is the Excel calculation F dot inverse, find the value, not the area, where the area is 0.025, 10 for degrees of freedom 1, 7 for degrees of freedom 2. To do the right one, it's F dot inverse dot right, RT. 0.025, 10 for degrees of freedom 1, 7 for degrees of freedom 2. 37B is a one-tail test. 37C is a one-tail test. That's why there's only one number in each of those. And notice, in that one, it says F inverse right 0.05. Alpha is equal to 0.05. Only in the two-tail do I split it in half. Questions? I will freely admit, doing this by hand's a pain in the ass. Excel is a lot easier here. So, I'm going to cheat. Quality control. Here is the data report from a drilling company. Manufacturing process drills holes in sheet metal that are supposed to be half a centimeter, 0.5000 centimeters. Before and after a new drill press is installed, we measure the hole diameter. 12 randomly selected pieces. Was the old drill just as consistent as the new drill? Do these have different variances? Now, I'm looking at this and I'm going, sure, right. How the hell am I supposed to know? Well, if I'm in Excel, I'm going to go and look at my data. Go back, data analysis. I look at my options. This is where the t-test and the z-tests were for means. But if I go up in this list, son of a gun, F-test 2 sample 4 variances. That's exactly the test I want to do. So I'm going to say, let's run this test. Click OK. Where's variable 1? Oh, that'll be the new drill. And I will even go so far as to include the name, and I'll check that labels box. Variable 2, old drill. Check the labels box. Alpha's 0.05. I go back and look at the problem. Yes, at alpha 0.05. Great. This is going to do what I want to do. And I'm going to stick all the information in a new page. Okay. That's illegible. Let's make that readable. Is the new process smaller variance? New process is 1. Old process is 2. I want to know if sigma 1 is smaller than sigma 2. This is a one-tail test. Okay. It did all the numbers for me. By the way, Excel always does a one-tail test. Always. For the F-test. Okay, here's my question. Do we have a smaller variance? Should we keep or reject our null hypothesis? Our null hypothesis was that there was no change, right? That the new and the old would be the same. What numbers up here tell me what to do? Two ways to do this. Say again? The p-value. What do I want my p-value to compare to? Less than 0.05. My p-value is 0.0003. That's a lot less than 0.05, isn't it? What's the other way I could have done this? Look at the p-value, or F calculated and F critical. Now, they just say F. There's no stat, calc, whatever. It's just the F that it came up with. And the F that it came up with is 0.1, and the critical is 0.35. I'm too far to the left, aren't I? I'm too small. There you go. Now, if we look carefully at the variances, the variance for the new drill is 3.2 times 10 to the negative 6th. Variance for the old drill is 3.2 times 10 to the negative 5th. The new drill is an order of magnitude better. It is 1/10 the variation of the old drill. Not only did you improve by putting in a new drill, you improved by a factor of 10. You made this variance much smaller. Now, I have no idea what you're building that you're drilling holes in metal. I don't know. But let me think about this. You're drilling holes that are 0.5 centimeter. How big is 0.5 centimeter? Not very big. That's a pretty required accuracy. Okay, maybe we're building car parts. You're drilling pistons into engine blocks? Well, piston screws, maybe. Pistons are pretty big, right? If those aren't machined very close to tolerance, then my engine goes boom. I don't want to be driving down the road while the engine goes boom. That's a bad thing. But, question for you. Is this statistically significant or practically important? That's where we ask the question, what did this new drill cost? If I spent $100 to improve my variance by 1 decimal place, that's pretty cheap. If I spent $100,000 to do this, that's expensive, but is it relatively expensive or moderately expensive? What's my business application here? I don't know. All I know is what I read here and they don't tell me. Most of the problems we will encounter, the critical piece of the pie, hardest part of the puzzle, write down the correct null hypothesis so we know what to test. Questions? Checking variances is so important that it has its own set of tests. And if you think about it, a lot of variance isn't just from one source. All I looked at was changing out this one drill. But the drill itself has several different pieces that go into how accurate it is, right? How many of you have used a drill press? A couple of us, good. Drill press has to be aligned properly. The bed has to be square. It has to be tared out. Then you have to look at whether you're centered in the chuck, whether the chuck is vibrating. There's all sorts of pieces that go into how accurate is this item. If I have all of these different interdependencies, how do they relate to each other? And the analysis of variation becomes, again, a lot easier to do in a computer than it is to do by hand. But that's a whole separate ball of wax. Questions? Analysis of variance, though, is our next chapter. And that means this is the end of chapter 10, which means two things. Your homework's due 2 class periods from now. That's Wednesday. But then we'll have finished chapters 8, 9, and 10. That's the exam material. And that exam is 1 week from today. I will, over the weekend, do the same thing I did for the last exam. Write up the things I think you're going to need, and I'm going to write the exam so I know what's on it. I will see you all on Monday. Have a wonderful weekend, everybody.